Thanks. So I would like also to thank the organizers of this PyData. This is my second year attending and giving a talk here, and it's been always great. And also thank you to stay here at the last block of the last day. I would like to talk about, not just about my Julia library, but I also would like to talk about a theory called light field theory that some of you might not heard about. So basically the main goal of this talk is to present a novel technique to reconstruct the depth map of a scene from a limited number of views. And what I mean by that is I want to recover the depth of some points in a scene from taking different pictures of the same scene. And this can be applied, and this is broadly applied in view synthesis and rendering for free viewpoint virtual reality, which is basically an immersive virtual reality where you can enter to a room from where you take the pictures and then move around the room because you know the depth of the different features in the room. I want to also explain the main building blocks of this technique, which is the light field and shirtlets, and show a free hardware-software implementation using Julia, Python, and Raspberry Pi. So last year, I don't know if some of you went to my talk. I basically talk about a Julia library that I developed for multidimensional signal processing, which is called generation.Jl. And this is going to be used here. So for a whole year, I think about some interesting applications of this library, and this was one that really caught my attention. So first of all, what is a light field? So how many of you have heard of this light field theory? Maybe none? Yeah, okay, cool. So this is based on the fact that light can be interpreted as a field. A field is just an assignment of a vector to each point in the space. This was proposed by Michael Faraday. Actually, nowadays we know that light can be interpreted both as a field or as a particle. So propagation of light rays in the 3D space can be completely described by a 7-dimensional continuous function that I will call L. And this 7-dimensional continuous function is known as the plenoptic function and basically describes the how much the light is expanding around the space in a point x, y, z with two 3-dimensional angles, theta and phi, and wavelength lambda and period tau. You can see this function. You can visualize it as in this diagram. So since computing a 7-dimensional function is really a complex task, one can actually reduce the complexity of the problem by simplifying the plenoptic function into a 4-dimensional function that is known as the light field. And this quantifies the intensity of static and monochromatic light rays propagated in half space. So basically what you do is you fix the wavelength. That's where the monochromatic comes from. You fix the one of the angles, and you also fix one of the special variables. There are different representations or different ways to parameterize this light field. One is, for example, taking points in a surface. A point in a surface is described by two variables, and then measuring the two angles, the 3-dimensional angles of the light that is going out of this point. The other one, you can actually also parameterize the light field by the intersection of the light rays in a sphere. 2 points that are also described by 4 parameters. And you can also describe the light field by the intersection of the light rays in 2 parallel planes. This is the approach that we were going to use today. This is called 2-plane parametrization. So basically, if you know the value of the light field in 2 parallel planes, all the points on 2 parallel planes, you basically can describe the whole light field. So, but how can you go from light field to 3D representation of the scene? Well, this is basically, this is based on a biological fact that the human brain generates the 3D depth perception of its surroundings by triangulating the points of a scene using the information coming from both eyes. So you basically have two planes that are the two image planes of the eyes, and you can triangulate back to the point, and that's how your brain know whether something is deep or not in the scenario. So the epipolar geometry is a mathematical geometry that basically generalizes the stereovision principle. And instead of just having two planes, you have basically a lot of different planes, and therefore you will have a better resolution of the light field. And it uses something called the epipolar constraint, where you analyze the object positions while assuming the knowledge of the camera motion. And here I'm talking about camera because what you do to actually recover light field, you basically sample the light field by taking different pictures of the scene that you want to recover. And you can assume that you know the position of the camera because you are moving the camera itself, and this reduces a lot the complexity of the problem. So here in this diagram, I have two planes, and I have a point in the scene, a point where I want to recover the depth. Yeah. So the plane that makes the point and the two length centers is called the epipolar plane, and points in one epipolar plane correspond to point in the intersection of one epipolar plane with one of the plane images correspond also to the intersection of the same epipolar plane to the other plane image. So it's really nice because you reduce this problem to a two-dimensional problem, basically. If you want to search for points in one line, you just need to search for the points in the same line corresponding to the intersection. So I'm going to use the assumption that we have a camera that is taking pictures of a scene and it moves in a straight line. This reduces a lot the way that you can describe the light field, because basically the epipolar plane just intersect each of the image planes in horizontal lines, and when you track the points in one of the horizontal lines around the different views, basically you get an image that is formed by these straight line structures. And this image is called epipolar plane image. From these straight line structures, you can actually recover directly the depth of the point, of the corresponding point. And that's why it's important to do this assumption. So how to recover the depth map with these epis that are that's how we call the epipolar plane images? Well, if you know the position of that point in each of the views, you can actually just compute the slope of the corresponding line where this point is, and this slope is completely related to the depth of the point by this formula. So, in order to have this kind of images, you need to take a lot of pictures, because there is something called the NumFOCUS criterion, which gives you basically a lower bound of the sampling rate of the images. And in order to have high resolution light fields, you basically need to take tons of high resolution pictures, and these high resolution pictures use a lot of memory, and it also the computational complexity to compute the slopes increases. So most of the people who is working on light field actually try to reduce the number of pictures you need to take to recover the depth map using something called the compressed light field. And that is what I want to talk about today. There are some examples of commercial light field cameras. The first one, this is called Nitro. I think that's the best known one in the world. And this comes from a startup in Silicon Valley. And it has, they actually did pretty well, and now Google bought them like last year. The other one, the one below, is called Raytrix. This is a German company, and it's mostly for industrial uses. So what I want to show you right now is an example of an image that was taken by the Litro camera, and how you can actually render the depth of the points. So this is an image. It looks like an image, but it's actually a set of a lot of images. How the Litro camera works is, instead of moving the camera, you have you have a microarray of lenses. So you take actually different pictures in this microarray. So when I click, for example, here, you change the focus of the picture. I can also click here, and you can actually move the focus of the picture wherever you want. I mean, this looks more like having fun, but actually it has some important applications. For example, in cinematography, because in cinematography, if you actually know the depth of all the points in your scenes, then you don't need to use green screens, because you can actually just separate each of the layers of the picture. And yeah, Litro tried to go in that direction and create a cinema camera, but it was too expensive. It didn't work out. So our approach here will be something that is known as sub-Nyquist reconstruction. The sub-Nyquist reconstruction basically reduces the lower bound of the sampling rate that I talk about. So instead of taking a lot of pictures, you take a sparse set of contiguous views. And the first image, this upper image, is the representation of this sparse set of different views in the epipolar plane images. This one that I show you, this one. So, of course, from here you cannot recover the lines, so you cannot compute the slope, because these actually don't form lines. So if you separate them accordingly to how you take the pictures, you can actually see that here you can see some lines, but of course we want to do this in the computer. We want that the computer recognizes the lines, so you cannot just ask for the computer to recognize these lines that are not really there. So you need to basically fill the gaps in between these lines somehow. This is an image processing task that is known as image inpainting. And I want to explain you broadly how this works. So the general setting of image inpainting is the task where you want to reconstruct an image that I'm calling F from just a known part of the image. So you lost some parts of the image. You have holes because the image can be old, or sometimes you don't sample the whole set, and you want to basically recover these holes and make sense of it. Yeah. So how to inpaint? Inpainting is based on a mathematical concept that is known as frame. A frame is just a generalization of orthonormal basis. So in the frame, you actually have the possibility to have recurrency, and this lets you compress images. So this basically lets you that the expansion of the image in this basis is sparse, that a lot of coefficients can be set as 0. And there are some results on sparse regularization and compressed sensing. Maybe some of you heard of compressed sensing, where it says that you can actually recover a signal or an image when it's sparse within a frame. You can recover it from a highly undetermined, non-adaptive linear measurements. In other words, you can inpaint an image by knowing a sparse representation of this image and just deleting the coefficients that are not so important. Some frames for images, some known frames for images are these. For example, Gabor frames, wavelet frames, which are the most widely known. And for example, the compression algorithm on JPEG 2000 is based on wavelet frames. Cubelet frames, and then the last one, sheeted frames, which was proposed by Gita Kutiniok and is the one that I mostly use. There is a result presented by Donahoe, which basically tells you how sparse can you actually get a frame on certain space. In this case, the space that I'm talking about is known as cartoon-like functions, and this is the space that best describe images. So what it says is like you cannot have a frame from which the projection of the image in this frame goes, so decays faster than n to the minus 1. The wavelets cannot sparsify pretty well images. They actually can just get n to the minus 1/2. And the reason for this is that wavelets just describe isotropic features of the images, so like squared blobs. So you need something that can describe also directional features of the images. So non-squared blobs, but like edges. And wavelets don't describe edges pretty well. That's why you need to use something that also changes the orientation of the elements. So basically, in this case, shearlet transform is just a transform or a filtering based on generating functions where what you basically do is you have a Windows function that will take the information, spatial information of the image, and then you also change the size of this Windows function. This is known as the scaling. This is the first matrix, and this change of size lets you have also spatial information of the image, like very localized spatial information of the image. In other terms, you can get some holes by knowing how this change of size behaves. And then you have something called the shearing, and the shearing just changes the orientation of these windows. So then you can also have directional information of the image. A slight modification of this system called the cone-adapted shearlet transform, where when you actually divide, say, the Fourier space in different cones, and then you take the shearlet transform in each of these cones, gets this bound given by Donoho. So basically, shearlets are a good frame to sparsify images, and as well as a good frame to compress images. And that's where I'm using it. So this is basically the followed pipeline that I use for depth map estimation. First of all, you acquire a rectify image sequence, which is taken in a straight line. So you basically take a camera, and you take images that are equally distance between another. And after that, you need to follow the points. You need to track the points in these images to see how fast they move in between the images. So this is the principle where that I use stock in the PyData Berlin images, where you can actually get the depth of the point by knowing the slope of the lines. And this slope of the lines is related to the velocity of the points in the sequence of the images. So points that are closer to you they move faster than points that are further away from you. Of course, for that, you need to somehow recognize features on the image. So not everything is easy to track. For example, in this blackboard, if you take a picture of this blackboard, you cannot track points in this blackboard. All of them look like the same. So you first of all need to detect points that are easy to track, and these points are corners. So I use the Shitomasi algorithm, which is implemented in OpenCV, this open source library for computer vision in Python. And then you need to track the points. For this, I just use the Lucas-Canade algorithm. I can give you, I did actually my master thesis on this, so I can give you also that if you want to know more of the mathematics behind these algorithms. And then you get, by just sampling sparsely the views of the scene, you get an initial sparse epipolar plane image from which you cannot yet recognize or detect the lines. And therefore, you need to reconstruct the dense version of this. You need to inpaint. You need to fill the gaps in between the views. And from that, I use shearlet inpainting. And then at the end, you need to basically detect the lines and then compute the slopes of the lines. And for that, I use the Hoff line transform. So for the parts of computer vision, like corner detection, point tracking, and depth map estimation, I use OpenCV in Python because the Julia version wasn't, the Julia API is not so good. And then for the whole other part, for let's say the inpainting, I use Julia. The data set that I use is a sequence of 101 rectified pictures of a scene generated by a professor in the Disney Research Center in Zurich. They also work with LightField. They actually have really nice results on high resolution LightField. The technical details of the physical setup, this is the physical setup. So, well, it's a Canon camera, and it's you move the Canon camera in a motorized linear stage that will take the picture, that will move the camera to each of the views that you want to get. And this is the first image, and this is the second image. It doesn't look so different, but with this, this is the first image, and this is the last image of the sequence. Doesn't look so different, but with this difference, you can actually recover the depth pretty well. So you don't really need to have a huge setup. These are the points that I could detect. There were actually, I think there were 340 points that I could detect and track. And this is the traces that they did in the different views until the last image. So in order to get the pictorial plane images that I talk about, from which you can compute the slopes and then the depth of the points, I took horizontal bands of points. And then if you track them the whole way until the last image, you get things like this, where the different colors are different features that I handpicked, but you don't really need to do that. And then if you just use, as I say, a sparse sampling of the scene, you get something like this, which reduces a lot the time and the complexity. So this is one example on the results. And then this is the sparse version, and this is the in-painted version that I get using shirtlets, and from which I can use Hawk transform to detect the lines. So these are the lines that I detected here, and then the corresponding depth map is basically this. And from here, it's just a color map representation of the depth map, where the lighter elements are the ones that are closer, and the darker elements are the ones that are not so close. Yeah. So yeah, I would like to show you just a little bit how this works. This is quite an early version of the project, because this is basically now my side project of the PhD. So I try to make it as reproducible as possible, but it's still not so stable. So basically the only libraries that I used was NumPy, CV, OpenCV, Matplotlib, Pandas, and yeah, basically that's it. So yeah. So there is a lot of examples actually in internet where you, for point tracking, using the Lucas-Canade algorithm, and you can get what gives you is basically gives you a list of the position of the points in each of the times where you track them. And this image was pretty nice because it has a lot of corners, but if I try also with an image that has not much corners, like this, and it can just track like 6 points. So this is not so nice for depth map recovery. Then after tracking the points, I basically, so I basically can get the sparse AP, and using the shirtlet inpainting, let me use. I get something like this. So maybe, since I have some time, I can explain you somehow how this inpainting works. So I will use this. So let's say that you have an image that has a tree here. And you have a hole here, where you don't know what is inside this hole. Intuitively it has a tree inside, but you don't really know. So you cannot really, you know that this image, almost all the features here, all the pixels here are equally important. So you need to transform this image to a space where you have a sparse representation, so where the coefficients or the values of this representation are mostly 0. And this is the shirtlets. So the shirtlets, basically what it does is they take just the edges here. most of the image are sparse in edges. Therefore, you can kill a lot of the other information of it. And then if the information of the image, if the information lost in this hole is not so important, then by just basically smoothing out iteratively around here, something called iterative part thresholding, you can actually recover this something that makes sense here. Yeah. Of course, if you have a face and you have an eye here and you lost one of the eyes, this method is not suitable to recover the eye. It will just recover, it will just fill with flesh here. Yes. So, yeah, so this project was basically motivated because when I tried to learn about these methods, like light field theory and how to implement them, I found that the bibliography that is available online is kind of obscure because it has a lot of like industrial interest behind, and I couldn't really get an open source code that tells you how to end-to-end reconstruct the depth map. That's why I did this project. So I tried to do it by myself, and I ended up finding out that wasn't that hard. And I also was motivated because most of the light field cameras are pretty expensive. They cost like at least 1,000 euros. And it really doesn't look like it should be so expensive because the mathematical concepts behind it are not so complex. So I think why not to do also a hardware implementation of this. So you just need Python, you need Julia, and you need a camera. That's the only thing you need basically. And Raspberry Pi has all of that. So Raspberry Pi has a Julia, has also Python, and there is a camera that you can connect to the Raspberry Pi, this thing. I actually have it here, but yeah. Right now it's still an early version, so a lot of things are crashing. But the idea here is, what I did was, you can take pictures using this camera and moving it in a track, and then the whole libraries that I use run inside here, and they do it automatically. So instead of paying 1,000 euros for a light field camera, this thing costs at most 70 euros. So the future work, what I would like to do in the future, if I have time, because not everybody wants you to do this. Like at least I asked to my advisor if I would like to do this, but she wasn't that sure that she could help me on this. So here, at least here in Berlin, I don't know where could I work with somebody that do light field. And the future work I like to do is basically dive in the rendering part. So far I can just compute the depth, but then I would like to render the scene. Because if you have the depth of the points or of the features, you can actually reconstruct the 3D version of the pictures that you're taking. And this is something that Google is doing right now. They use something called, they have a project called Project Tango, and they also have other projects where they are trying to create immersive media, so you can interact 3D in a 3D setting with created environments. And yeah, basically, I would like just to show you that this field is quite interesting, and it's not really so hard to enter, and I think has a lot of industrial opportunities. And yeah, that should be it. Thank you for your attention.
Thank you, Hector, for a very interesting talk. Do we have any questions from audience?
Thanks a lot for the great presentation, Hector.
Thanks.
So photography is a little bit my passion, and I was observing pretty closely the launch of the Lightro camera, probably 4 years ago, 5 years ago, and then nothing happened really. And one of the things I observed was, the resolution was fairly poor, and there wasn't, in terms of it's something you try, and you play around with it a couple of times, and then you're done. It's kind of nice to change the focus, but the application was missing, and also the resolution. If you do this with your Raspberry Pi, do you get the normal resolution of the camera, or you haven't done that yet, right? The reconstruction.
Yes, I have done it.
You have done it.
Yes.
Can you show us a picture?
Yes, wait. I have right now not an example with the Raspberry Pi camera, but I have this example of this picture that, this picture is of resolution 512 times 512, and you can do the reconstruction using this sequence of pictures. So it will apply the same for the Raspberry camera pictures.
But this is, you use the Canon Mark IV, so
yeah,
the original resolution is much higher. What do you do with the rest of the information?
I subsample the images to get a lower resolution. So far, this algorithm works for any resolution. It will just take more time for higher resolutions, because then you need to track more points. You have more points to track. So there is not really a limit of the resolution.
Okay.
Maybe just the time. And also the problem with the Raspberry Pi basically is that this is the Raspberry Pi 3, and it has 1 GB of RAM, and you cannot really fit a lot of stuff there. So what I needed to do was to basically, for example, the filters that I use for shillets, I needed to first create them somewhere else, and then save them in a HTF5 file, and then just put them inside here. They work for any image, so you don't really need to compute them on the fly. And that's are some of the limitations of the Raspberry Pi, and it's crashing a lot. That's really a problem. Let's say 2 or 3 times that I try to run the reconstruction in the Raspberry Pi crashes.
And the other question I had was just from a contrast perspective. You mentioned the blackboard, which obviously you cannot differentiate with your shearlet, and the Lightro, they do it by the microarray, where they detect the angle of the light initially. Yes. I think so. They don't have that limitation.
Yes, that's
What are your
true.
thoughts? How do you want to further develop that area?
Yeah, that's true. My approach is poor in the sense when you don't have too much corners to track. And yeah, I don't know. I was mostly inspired on the approach of the Disney Research Center in Zurich, and they use this, so they track points. So I'm not. I think the people in Litro, they get the direction of the light rays by this microarray of lenses. This doesn't work here. So yeah, that's a downside. Yeah. Yeah, I'm not completely sure how the Lightro camera works. I know there is the PhD thesis of Ren Ng, the guy who was the CEO of Lightro, and I think he explains pretty well there the rendering, and that will be my next step, to read how to render LightField. But yeah, I am not. Thanks.
Do you have any other questions? Then maybe I'll ask you, do you have any plan to release the hardware that you created, and if it's like so competitive in comparison with commercial stuff, do you think that it would be worth to try to make some embedded device out of it and ship it to market?
Actually, I think there is a lot of potential in that, because also it's not, this hardware, this low-cost camera, doesn't have just the possibility of doing light field reconstruction, but you also have a lot of different stuff that are already implemented in OpenCV that are already used in Raspberry Pi cameras. Mm-hmm. So you will have a super camera with low RAM, basically. But I was mostly inspired by the open source community, and as such, I just open sourced everything.
Wonderful.
So anybody that wants to apply it can just do it. I don't plan to sell or anything.
That's really cool. Thank you. And maybe one more thing that I'd like to ask, maybe not directly related to the whole project, but in general, why Julia?
Okay. Yeah. So this is mostly historical. So I studied my bachelor in Mexico, and my supervisor there was a huge Julia developer. I mean, fan, let's say. He's very involved in the Julia project, and he convinced me to use Julia, and I really liked it. I'm not completely so close-minded to just say Julia is the greatest thing. So I use my daily life different things, but I do enjoy to program in Julia, and it's for a lot of applications it's super easy and fast. So yeah, I mean, I think, for example, for this signal processing library, ShearLab, it was pretty easy to implement it in Julia, and so far is the fastest implementation of this shearlet transform, and it was really easy to do it. So yeah, I think it's also a good programming language to start with if you have no experience with programming. Python and Julia are very similar, so if you program in Python, it's completely automatic. You can program in Julia. And MATLAB. I mean, Julia was designed for mathematicians to make them stop using MATLAB, basically. Yeah. And that's, I like that idea.
Thanks a lot. So we still have plenty of time, guys. Any other questions from the audience? Then once again, thank you. Oh, sorry, I didn't see.
So thanks for the talk. I was wondering, in the setup you have there, the way I understood it, you need to know pretty exactly how the camera moved and how the pictures were taken in relation one to another. For end-user applications, you usually wouldn't have that. So if you try to do that on a smartphone camera, for example, is that a next step for you, or can you comment on how possible or impossible that is with this technique?
So my approach explicitly uses views or photos taken by a camera who moves in a straight line, and a straight line which is actually orthonormal to the lens axis. So that's the only way it's going to work. That's also one of the downsides. So in a smartphone, you will need then that the camera of the smartphone, you can move in a straight line along the smartphone. That will work, but that's kind of cringe. That's kind of it's not so comfortable for sure. So yeah, it doesn't really work for. I mean, my idea was to have in this thing to have a track which moves in a straight line, and by doing that, I basically broke the camera. So yeah, I'm not completely sure yet how to make it easy in an easier way. I mean, in this setup, it's huge. So you have a track, which is huge, and also a camera. So of course that is not for for commercial applications. Yeah. And maybe other applications that I didn't. Okay. Yeah. Sure. It was just to mention other applications that I didn't say of LightField. For example, there is something called LightField microscopy, where you can, if you recover the light field of an image in a microscope with different focus, then you can. I think some people use this to have so to separate elements in the objective of the microscope. And yeah, also I thought about this cinematography application where you can separate the layers of the images, and then you don't need to use a green screen and things like that. That will reduce the cost of post-processing of cinematography, because, for example, if you are out of focus, you are not really you're not really worried about, because you can change the focus anyway. Yes. Please.
Yeah, but just a follow-up question on that comment. If you, for example, with your DSLR take the picture, you want to make sure that everything is in focus.
Yes,
which is
sure.
kind of contradictory to using a larger sensor at some point, and also to allow short exposure times.
And you also need rectified images.
Right.
So you need to first rectify them. That's also, yeah, that's true. There's a lot of downsides, but it still was a kind of a cool project to do.
Very cool.
Any more questions? Then once again, thank you very much for the talks. And now, guys, in